Hello friends, this is a tutorial on the bending analysis of some composite cylindrical shell in Abacus. I am Sranishkar, a research scholar at the Smart Structures and Materials Lab of the Department of Mechanical Engineering, IIT Guwahati, and I am working on the development of analytical solution for piezoelectric smart cell structures under the supervision of Dr. Poonam Kumari. So today we will be solving the following problem. Find the three-dimensional stresses and displacements of the following cylindrical cells made of laminated composites and subjected to following pressure and boundary conditions. A thick shell of thickness factor S 4 is considered of axial length 4 times of S and circumferential span of pi by 4. It is cross-pile laminate with 90-090 scheme and is simply supported at its circumferential boundaries. A sinusoidal normal load is considered at its inner surface, and the material properties are those of a carbon epoxy, where the constants are listed below. The fiber orientation of the plies is with respect to the z axis of the cylinder. So the problem looks something like this, and we will go for the new model. This is the model window. This is the model tree, and these are the menu bar and the toolbar respectively. First of all, we have to create the set work directory and set the work, and you can browse the directory from there. Click OK. Then we have to set the module to part and create a part. The part name is given as shell here, and the modeling space is 3D. It is a type of deformable and solid extrusion type. These are the center lines, construction lines, the horizontal construction line and the vertical construction line, and the two oblique construction lines at making a 45-degree angle is set. Then the arc is selected, and we go for the dimensioning. While we go for the dimensioning, we see that the construction lines shift. That is why we need to fix the construction lines so that the axis of the cylindrical parallel passes through the origin. Now we are again dimensioning for the inner surface of the panel at 3.5 units. Then the uh, outer surface is at the distance of 1 unit, which is the thickness h, and close the sketch by a sketch tool. This is the extrusion length, which is given as for 6. Then we have to create the plies through offset tool at a distance of 0.333, and the other ply at a distance of 0.667. So 3 equal plies have been made. Create the cylindrical coordinate. As by default it is rectangular coordinate in xyz. The coordinate origin lies at 008. The radial distance is at 048, and the theta point lies at -408. Then go to the property module, create a material, carbon epoxy. Go to mechanical elasticity, elastic, and set to engineering constants. Give the 9 engineering constants: E1, E2, E3. New 1 2, new 1 3, new 2 3, and G1 2, G1 3, and G2 3 respectively. So a material is created. After it, a section is created for the corresponding material, which is solid and homogeneous type, and make sure the material is selected. Then you have to assign the section to the parts of the body, and now the material orientation is set. Select the outer two as both are 90-degree. Go to discrete type and give the normal axis to the surface. Select the surface, and the primary axis of material is taken as a, a axis of the datum, which we take as z axis. And with respect to the third axis, we give a rotation of 90-degree or 90-degree ply. And similarly for the middle 0-degree ply, go for discrete, and same normal and principal axis are set. However, this time no rotation is required. Then go to assembly. In assembly, take independent. Okay. And in the step module, create a static step for static analysis, and make sure the nonlinear geometry is off. Go to the load module. Here in the load, we will create a sinusoidal load, pressure load, mechanical, on the inner surface. Give the type of give the expression for the sinusoidal load with respect to the coordinate system, and select the expressions from the drop down from the menus. And R, TH and Z are the axes with respect to which now select the field and give the magnitude as 1. Go for the setting of boundary conditions, displacement and rotation type on the circumferential edges. With respect to the coordinate system, take u1 and u3, that is ur and uz as 0. This is the paper according to which we are solving the problem. That is ur and uz at theta is equal theta edges is taken to be 0, and u theta and ur is 0 along the z axis. Click OK. Then for the other z axial boundaries, select the faces. With respect to the cylindrical coordinate, give ur and u theta as 0. Then go for the mesh module. If create a seed edges, we will put seed on the edges or nodes on the edges. And for this, it is convenient to go to wireframe view. Give the number of nodes as 20 along the z, as it is a plane strain problem. So along z, number of elements is doesn't depend on the number of nodes along the z. And set the number of Once all the nodes have been placed, go to define the type of elements, and this is 3D trace elements with quadratic type, so that this and mesh the part. So all the modules have been done. However, if you want to decide what all variables you need to calculate, go to field output request. Here you can see the stresses and displacements have been ticked. You can tick any other requirement as per requirements, and the field uh, expression you can edit here. Then create a job, the job module. You can, if the number of nodes are higher, you can go for multiple processors. However, it is not required here. So finally, we submit the job for analysis. So after the job has been analyzed, has been, we can see the results in the visualization module. Here we can see the orientation of the plies to ensure that it is properly oriented, and this is the uh, undeformed uh, stress and displacement plots. However, these are results with respect to the global coordinate, so we need to transform it to the local coordinate, which is our cylindrical coordinate. And okay, so for the transverse displacement, we will first, for obtaining the for checking uh, the value at any node, we can go by this process at query tool, and in the transverse displacement we see that this has been obtained. However, the values need to be non-dimensionalized as per this formula. So we need to non-dimensionalize the actual displacement value, which is quite small. Similarly, for the stresses, the sigma z at the middle of the inner surface and middle of the outer surface, as at these locations the stresses are high, and these are also non-dimensionalized as per the formula. Then go for the sigma theta at the same locations. And finally the transverse stress sigma r theta at the edge, at the middle of the edge. Now these stresses are compared with the exact solution obtained in this paper for s equal to 4, which we are solving for. We can see that the numerical results deviate by certain degree of by by are deviating. However, we can infer that our modeling is proper and the results can be uh, conversed after convergence study. So now in case we need to plot the stresses or the displacements at every node, we have to create a path. We have to create a circular path here, go for circumferential path and go for 3-point arc. Let us suppose we are doing it for a sigma r. So we are taking any 3 points on the arc for which we need to create the path, and this is the angle, that is pi by 4. So the path is created. Now we can go for the xy plot along the path on the undeformed body, and normalized distance can be done, or else we can directly save the xy points, which we can obtain in a .rpt file, which is created in the working directory, and we can append these variables in the file, or else we can see the plot over here and we can ensure that the values are different. Thank you.